Hello, and thank you for tuning into our presentation. We are Team 67, which is composed of Derek, who's currently speaking on the left, Eric, Josh, and Chris. And today we're going to be showcasing our team's final design for the Mars Cargo Mobility System project, or the MACRO for short. We're also going to be guiding you through our general design process that led us to the beautiful robot that you can see on the right side of your screen, as well as highlight some of the strengths and weaknesses of our team's final design. So sit back, relax, and enjoy the presentation. For anyone uninitiated, the main goal of this project was to create an autonomous line-finding robot, aka the MACRO, that is capable of delivering 3 different types of cargo to 3 different landing sites. The MACRO would need to be able to properly recognize and handle various different types of obstacles, as well as deal with line breaks in the guidelines, which you can see an example of in the picture of the course shown. Now, obviously, we were only able to test this out on a track on the floor of a gym, but the eventual goal of the project was to create a prototype that could one day be scaled up to be functional on Mars, including dealing with Martian environment and just any other issues that would come with being on a different planet. Now, as you can imagine, there are many different aspects of the project to be considerate of, so the team had to be extremely organized throughout the entire process. To keep everyone accountable and consistent, the team split into 4 separate roles. Eric was the meeting coordinator who was tasked with creating an agenda for every meeting, and I, Derek, was the recorder who was responsible for recording everything that happened in our meeting, which mainly showcased itself in the design notebook, which ended up being over 30 pages long that documented over 36 hours of official team meeting. Josh was the timekeeper who kept us on track, and Chris was the encourager who kept us in good spirits even after tough days of prototyping. The design notebook, which I've already mentioned, was put in place to keep a close log of everything that the team did, which meant lots of note and picture taking. In order to be even more organized, the team created a Gantt chart, which you can see on the side here, that gave the group a timeline for when things were to be accomplished, and who was responsible for what with which role. Taking all of these measures allowed the team to stay on top of every single aspect of the project, and the team certainly would have failed without these measures put into place.
Design management, needs finding, functional block diagram. At the beginning of the project, our team brainstormed and synthesized a functional block diagram in order to help ourselves understand the different aspects of design that we need to address. This ended up being essential to the hardware element of the build, as it helped us think through the elements that went into the design. Also, after reading the description of the problem that our team was assigned with solving and looking at the requirement that the prototype needed to meet in order to be considered for scaling, we developed a needs list so that we could have a condensed scientific display of how our vehicle needed to be able to perform. Design philosophy, mechanics. After considering the functional block diagram and the needs list, we concluded that the prototype would have 3 primary physical systems: drivetrain, cargo system, and sensors. Drivetrain. After considering the functional block diagram and the needs list, we concluded that the drivetrain would be the most important element of the design. Therefore, we designed the robot around this primary component. We progressed through 3 primary drivetrain formats as we developed and tested the robot. First, a 4-wheel, 3-motor design in which one motor powered each of the back wheels and a motor powering the front 2 wheels. Second, a 6-wheel design in which the robot has 3 wheels on each side. The middle 2 wheels were driven by separate motors, while the back 2 were powered by the same motor and the front 2 were left unpowered. The third iteration only slightly differed from the second, as we replaced the 2 unpowered wheels at the front of the robot with 1 central unpowered wheel. Cargo system. The second element we focused on was the cargo system. The first design we tested consisted of a track on which the cargo sat during travel. At the desired destination, the track rotated and the cargo was pushed from the robot. However, the system proved unstable when tested. Therefore, we developed an oscillating subframe to deliver the cargo. A bed was made on which the cargo sat. Then a subframe was made to encase the 4 sides of the cargo. When functioning, the subframe oscillated back and forth slowly. When extended, the subframe pushed the cargo off the bed and allowed the cargo to drop to the ground. After considering the other primary design elements of the prototype, we concluded that the sensors would be the least difficult to implement. Therefore, we saved them for last. The primary goals in placing the sensors was to avoid interfering with the moving parts of the build and to optimize their functionality in order to improve code performance.
Developing the software to fluidly integrate with the hardware and physical macro, while allowing the entire system to function autonomously following its deployment, proved to be an extremely challenging task. These difficulties were able to be mitigated with the utilization of a flowchart and numerous iterations of the software as it was developed in parallel with the physical vehicle. The flowchart is a critical aspect of software development as it allows the programmer to visualize the flow of logic and the various elements that must be incorporated in the Python script. While the flowchart was being generated, template scripts were developed to assess the capabilities and performance of the sensors and motors to allow for the optimization and integration of the use of these hardware components in the code. Following the completion of the flowchart and hardware performance assessments, the software was developed in numerous iterations to reflect the capabilities of the physical macro at any given moment. These iterations focused on generating a Python script to allow the vehicle to navigate through the course, handle the presence of obstacles, locate the designated cargo location and deliver the cargo, and ultimately refine the performance of the vehicle. At the conclusion of developing these iterations of the software, the code would be uploaded to the Raspberry Pi responsible for controlling the vehicle, and the Python script would be run on this control module in order to demonstrate the abilities of the software and the hardware and clearly depict which aspects of the macro required refinements and alterations. Team 67 is very content with the performance of the macro developed by these engineers and have identified numerous positive attributes of the vehicle. These attributes include the vehicle's consistent ability to navigate the course, the reliable performance of the cargo containment and release mechanisms, and the adaptability of the software to reflect the various potential requirements. The algorithm for enabling the vehicle to follow the path of the course was very effective and accurate, allowing the vehicle to consistently navigate the course in an exceptional manner and precisely execute the necessary navigational maneuvers at any given moment. The cargo containment and release mechanisms ensured that the vehicle was capable of transporting the cargo and delivering the cargo safely to the intended cargo location, despite the challenges and obstacles present during the course. The adaptability of the software allowed the vehicle to reflect any alterations to the mission requirements and fit any possible scenarios provided. Ultimately, the vehicle excelled in these aspects of the demonstration, and these positive attributes significantly increased the potential for Team 67's macro to be selected for this mission.
In regards to the negative attributes of the macro, there are a few key points that need to be mentioned. Firstly, the vehicle has a weak drivetrain system for the middle two wheels. During quick turns or high speeds, the wheels could become detached from the axle due to a weak securing mechanism for the wheels. Another negative of this macro design is the unreliable magnetic detection system. The Hall sensor was used to let the macro know when it was approaching the magnet. However, the Hall sensor worked with limited success. In our test, the Hall sensor could only reliably detect a magnet that was 1 to 2 centimeters away from the sensor. But given that there were ground clearance considerations, the team had to mount the sensor at 3 centimeters above the ground. Therefore, the macro's magnetic detection would work with varying success. Finally, the macro had poor hill climbing ability, especially if the hill was approached at an angle. With a steep hill, the macro would lose grip with its main middle drive wheels and have to rely on the back motor to get up the hill. Also, if the hill was approached at an angle, the macro would only have one drive wheel to get up the hill. This forced the team to use 75% motor power to get over the hill, compared with 40% motor power used on level ground. In order to scale up the macro to a full-size vehicle that functions on Mars, there are a couple important considerations to be made. First, the traction on the Martian surface will be much reduced due to the lower gravity. This could be addressed by giving the vehicle tires with more grip, as well as adding in a suspension system to ensure that all wheels make continuous contact with the ground. Another consideration is the battery, which will need to be shielded from the harsh temperatures on Mars so the battery can operate in an optimal temperature range. A solution for this would be to enclose the battery in thermally insulated material so that heat loss will be reduced. Finally, the sensors will need to be protected and adjusted so that they are better suited for Martian conditions. This would include a cleaning mechanism for the sensors to prevent dust buildup, as well as a protective housing around the sensor electronics. Overall, Team 67 is very pleased with the outcome of the macro design and believe that it has many great aspects that make it very well suited for the task. The vehicle closely follows a philosophy of simplicity and reliability, which makes it a very scalable and adaptable design. For the majority of tests, the macro performed as desired and completed the task successfully. The main design choice that did not work as expected was the decision to use the Hall sensor for the magnetic field detection. Because of the range deficiency with the Hall sensor, the macro had difficulty detecting the magnet and therefore releasing the cargo. This issue could be addressed by using a more powerful sensor such as an IMU or equivalent. Another thing that didn't go according to plan was the cargo release system, which knocked over the cargo in the tests. In a future iteration of this design, this could easily be addressed by raising the back fence so that it would no longer hit the top of the cargo. With these issues addressed, the vehicle will be easily scaled up to be deployed on Mars and to complete the mission.